Okay, in this video I'm going to talk about tangential quadrilaterals, or they're also called circumscribed quadrilaterals, and the sums of their opposite sides, and this is also known as Pitot's theorem. So basically we have a quadrilateral for which there is an incircle. So there is a circle that is inscribed into this quadrilateral. In other words, that it tangents, like it touches all sides of the quadrilateral. So such quadrilaterals are called tangential or circumscribed. So yeah, something like this. And basically, so A, B, C, D, and basically the Pitot theorem says that for such a quadrilateral we have AB plus CD is equal to BC plus AD. So the sums of the opposite sides are equal to each other. And there is a converse statement that says that if we have this equality, then for any quadrilateral, then this quadrilateral must be tangential. But the Pitot theorem is just to one side, like only the statement that if the quadrilateral is tangential, then this holds, and the converse statement is just another theorem. So okay, so let's prove this. So basically, we are going to use the fact that if we have a tangent from two tangents from the same point to a circle, then these two segments are equal to each other. Like I proved this in a separate video. It's quite an easy proof. Yeah, so like in this in this picture we have this segments equal, this segments equal, this segments equal, and this segments equal, right? So if we denote them, let's say by x, this would be y, z and t, then we have the sum of AB plus CD would be equal to y plus x, that is AB, y plus x plus z plus t, that would be CD, and the sum of BC and AD would be equal to, so BC would be x plus t, and the AD would be y plus z. Would be y plus z. So, and we see that this sum is equal to this sum because they're both equal to x plus y plus z plus t, and this is equal to x plus y plus z plus t. So these expressions are equal between each other, therefore, so from this we conclude that, so this out the question mark, we don't know yet, like we didn't know yet that they're equal, but from this, from the equality of these two expressions, we conclude that AB plus CD is equal to BC plus AD. So the theorem is proven. So now the opposite, the converse statement is a little more difficult to prove. So basically, let's write this is a separate theorem. So so we have a quadrilateral ABCD such that AB plus CD is equal to AD plus BC. And from this it follows that ABCD is tangential. So basically we draw this quadrilateral. ABCD, and we consider in circle of the triangle. So let's continue this until the intersection point somewhere, and we consider this would be, this intersection point would be P, and we consider the in circle. So consider the in circle of the triangle PCD, right? So it's basically a circle that touches the lines BC, CD, and AD. Like we know, we know that any triangle has an in-circle. So for any three lines, like these lines BC, CD, and AD, there is a circle that touches all of them. So, but it might not touch the fourth side, AB, right? So that's not a problem. Yeah, the point P, we actually don't need it. But what we will do is we draw a tangent from B to this circle. So the one tangent is BC, but we draw another line that would be tangent to this circle. So something like this. It touches this circle. And we denote this intersection point of this tangent with the line AD. We denote it by A prime. A prime. So this point is A prime. Or let me write it here. A prime. Yeah. So now we know from the already proven Pitot theorem, we know that the sum of the opposite side is, so now the quadrilateral A prime BCD is tangential by construction. Is tangential. So by the already proven Pitot theorem, we have that A prime B plus CD is equal to BC plus AD, right? So, but we know from the statement of the theorem that this holds, right? So when we subtract one from the other, what we get, BC plus A prime D, excuse me. Yeah, not AD, but A prime D, of course. Yeah. So when we subtract one from the other, so we have from the original statement that AB plus CD is equal to BC plus AD, and from these two we conclude that basically subtract one from the other, we conclude that AB minus A prime B is equal to AD minus A prime D, right? So now so now we notice that AD minus A prime D, so on the picture, so this is AD, this large side, and this is A prime D, the smaller side. So since they're on the same line, so the difference between them is simply this segment A prime. So this would be equal to A prime. A prime, and so to rewrite this further, this can be written as AB is equal to A prime B plus A prime, right? So we moved the minus A prime B to the right hand side. So okay, so let's look at the picture. So AB is equal to, so AB is equal to A prime B plus A prime. So just to draw separately there, so we have AB here, the segment AB, and this is A prime. So AB is equal to A prime B, this, plus A prime. So from this, so like by the triangle inequality, we have that any side in the triangle is greater or equal than the sum of two other sides. So A prime B plus A prime, so exactly this expression. And the equality holds only when the triangle degenerates, so when the 3 points lie on the same line. So this is the triangle inequality, right? Triangle inequality. And so because we have this equality here, from this we conclude by the triangle inequality that A prime lies on AB. So the A prime lies on AB. But the only case when this is possible is when, so A prime was constructed as the intersection point of the tangent B from B to this circle with the line AD. So the only case when, so like by construction it lies on the line AD, right? So if it also lies on the line AB, as we proved, so the only possibility when this can happen is when A prime is equal to A, when this is the same point. So but A prime also belongs to AD. D is somewhere here on this picture. So, and from these two we conclude that A prime is equal to A, because the intersection point of these two lines is only the point A. So, and from this we immediately conclude that because A prime BCD, quadrilateral A prime BCD was tangential, and since A is equal to A prime, so therefore the original ABCD is also tangential. And this concludes the proof of the theorem.